What's going on, YouTube? Welcome back to another Tutortopia video. So in today's video, we'll be going over higher order ordinary differential equations. So first off, what are higher order ordinary differential equations? So our previous differential equations have been in the form y prime plus some stuff equals some more stuff. So we notice that right here, our highest order of our derivative is actually just the first prime, right? So a higher order ordinary differential equation could be written as like y double prime equals, for instance, like say 0 or something like that. So this would be considered a second order differential equation because there is two derivatives. So two derivatives. Okay, and then so the question is, how do we solve these higher order ordinary differential equations? So let us have a higher order differential equation, and then let's consider it a linear case. So let's just have a y double prime plus b y prime plus cy equals 0. And then let's just have it be homogeneous, and then homogeneous means that this side with our like functions y is just equal to 0. Okay, so how would we solve this? So someone already did solve it. So we know that we can just say guess. So we guess our solution first. So we guess that it's in the form e to the lambda y. Okay, or let's say lambda x. So we say y equals e to the lambda x. Okay, so now we know from this that y prime is equal to lambda e lambda x, and y double prime is equal to lambda squared e lambda x. Okay, so plugging these back in to this equation right here, we get a times y double prime, lambda squared e lambda x, b lambda e lambda x, c e to the lambda x is equal to 0. Okay, so for this we can just pull out all of our e to the lambda x's, and we get this quadratic in this case since it's a second order. So this is what we call our characteristic polynomial. So we can easily solve this for lambda, right? So we have lambda equals negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Okay, so now we can plug this back into our guess, which was right here. Let's do a different color. So we plug this back into our guess, and we get y is either equal to e to the, I'm going to say lambda plus x. So this means that the plus is in the square root, or lambda is equal to e to the lambda minus x. Okay? And then what's really cool about this is that we can have a superposition of these two functions. Let's call it like 1 and 2. So that means that my actual function, or solution to this differential equation, is y of x equals some constant times our number 1, which is going to be equal to e to the lambda plus x, plus some other constant, e to the lambda minus x. And then just writing these out, this is just equal to c1 e to the negative b plus root b squared minus 4ac all over 2a plus c2 e to the negative b minus square root b squared minus 4ac all over, all over 2a. Cool. So this is our general solution to our y prime. Okay, so now I think something helpful would just be to see an example with, instead of using a, b, and c's, we use actual numbers. So let's have y double prime plus y is equal to 0. Okay, So then we can do lambda squared plus 1 is equal to 0. So we don't have to derive what I did up here every time. I just kind of wanted to show you where the characteristic polynomial came from. But after you see it the first time, you can just kind of use it. So my second derivative goes to the second order of lambda, and then I put my coefficient, which is just 1, in front of my lambda squared. Likewise, this has a 0 order, so it's lambda to the 0. Anything to the 0 is equal to 1. My coefficient in front of here is a 1, so I get this characteristic polynomial. Okay, so now I can easily solve this. So it goes lambda equals plus or minus I. Okay, so after we have lambda equals plus or minus I, we can plug that back in. So then we get y of x is equal to c1 e to the lambda 1. So what's my lambda 1? I'll just call it plus I times x, plus c2 e to the negative I times x, which is my lambda 2. So I'll call this lambda 1, and this is my lambda 2. Cool. So if let's just say c1 is equal to c2, then we see that this is actually e ix plus e minus ix, which is actually equal to 2 cosine of x. Cool. So this is actually an oscillation function. So if you guys have taken like a physics class, this is basically the equations where you're getting your oscillation functions from. And then they usually can be written as like cosine of x. Okay, so now let's do another one. So let's say that we have a third order polynomial instead of a second order. So let's do y triple prime plus y double prime plus y prime is equal to 0. Okay, so this goes to lambda cubed, right? Plus lambda squared plus lambda is equal to 0. Okay, so can I solve this cubic equation? I can, because I can just pull out a lambda, and then I note that it's lambda squared plus lambda plus 1 equals 0. So therefore my lambda must equal 0, or lambda squared plus lambda plus 1 must equal 0. I can solve for that. So we go, let's see, what does that solve to? So we can go negative 1 plus or minus 1 squared minus 4 times a times c all over 2. Okay, so that equals negative 1 plus or minus root negative 3 all over 2. Okay, so then we'll call this lambda 2 and lambda 3, and we'll call this lambda 1. Okay, so then again, my y of x is just going to be equal to c1 e to the lambda 1, which is 0 times x, plus c2 e to the lambda 2. Lambda 2 in this case, I'll just choose the plus, plus c3 e to the lambda 3, which is negative 1 minus negative root 3 all over 2. Cool. And then in order to solve for these three constants, 1, 2, and 3, we're just going to be need to given the sometimes they're called boundary value, initial conditions usually called, is what they're called. So we have like y prime at 0, y at 0, and y double prime at 0, for instance, is what they could give us. And then using these three, 1, 2, 3, let's just say that those are what the values are. Using these three values, we can plug it back into here and then solve for C1, C2, and C3. Okay? So there's actually one special thing that can happen in higher order differential equations that can't happen in lower order differential equations. So that's something called a double root. So let's have y double prime plus 2y prime plus y equals 0. Okay, so this would go into lambda squared plus 2 lambda plus 1 is equal to 0. And then we notice that this is actually a binomial factorization. So we say lambda plus 1 squared must equal 0, which then goes to lambda must equal -1 with multiplicity 2. I'm just going to write mult 2 because it's squared, you see right here. So what happens here is we would write down y of x is equal to c1 e to the lambda 1x plus c2 e lambda 2x, which is just going to be equal to c1 e to the -1x plus c2 e to the -1x. But these two are now the same, so this is just equal to c1 plus c2 e to the -1x, which two constants written together, like 1 plus 2, is just equal to another constant. So we can actually write this as just some other constant. I'll just arbitrarily name it c3 e to the -x. And this is not, this isn't really complex enough to describe this equation right here kind of intuitively. We're like, oh, this is a relatively complex equation, right? You don't go over it in like high school. So it should probably have a harder answer than just e to the -x. So what actually happens when you have a multiplicity of a root right here, so I'll cross all this off in red. So what you actually have is y to the x equals c1 e to the lambda x plus c2, and then we just slap on an x right here, e to the lambda x. So in this case it'd be c1 e to the -x plus c2 x times e to the -x. So we just slap on however many like polynomial, we just slap on as many of these as we have like multiplicity of our characteristic equation, which is up here. So multiplicity 2 means that we have the first term and then we just add on one more x term. Okay, so let us do one more example problem because I know that can be a little weird. Let me try to think of one. So example, and let's try to do one with, let's do y triple prime plus y double prime 2y double prime plus y prime is equal to 0. So again, I'm kind of cheating. Oh, you know what I could do? We could use 3y double prime, 3y prime plus y is equal to 0. Okay, so my characteristic equation, or polynomial, is going to be lambda cubed 3 lambda squared plus 3 lambda plus 1 is equal to 0. Okay, so what does this solve to? Well, again, I chose this specifically for this. This is actually equal to lambda plus 1 cubed equals 0, which then goes to lambda equals -1 with multiplicity equal to 3 this time. Okay, so using that, I have y of x is equal to c1 e to the -x plus c2 x e to the -x plus c3 x squared e to the -x. So this can also be written as c1 plus c2x plus c3 x squared e to the -x. So this is sometimes how it's written. So you can see the multiplicity of 3 comes in the order of this polynomial. So this is a polynomial order 2, right? Because the highest power is 2. But, and then in the last case up here, we could write this as c1 plus c2x e to the -x. So this is again a poly of order 1. So the polynomial order right here, so like the coefficient in front of your e to the lambda x term, is just going to be the multiplicity. So equals multiplicity minus 1 of your lambda. Okay, so that is how you can do some basic second order and third order ordinary linear differential equations. That is all I have for you in this video. In the next video, I'll be going over inhomogeneous or non-homogeneous differential equations, and I hope to see you there.